When we first started talking about forces, we didn't really worry about dynamic systems right away. We just started with static systems. We said, let's take a situation and figure out how to balance the forces so that we get an equilibrium scenario. And that was translational equilibrium. Let me look at this though. This is going to be an example of rotational equilibrium. If I have an object like this, and I stick an axis right in the middle of it, I can apply a force over here, let's say 100 newtons, and I can apply a force over here of 100 newtons. The total net force on my object is 100 newtons up, 100 newtons down. So if I call upward my translationally positive direction, my total force is 100 newtons minus 100 newtons equals 0. This thing is in translational equilibrium. But there's a problem, and you know there is. Looking at this thing, you could tell me that is going to go somewhere. It's going to do something, right? If I push up on the left side with 100 newtons and down on the right side with 100 newtons, then what's going to happen? Well, this bar is going to start spinning. That's not a translational equilibrium issue. We are still fine there. The net force on this bar is 0, so there will be no acceleration of the center of mass of the system. Center of mass of the system is right here in the middle at the axis, so our center of mass is stationary, or at least inertial. If it was moving, it'll keep moving. So our center of mass is stationary, but we do have torque to contend with now. So if this is a distance of, let's say, 2 meters, and this is a distance of 2 meters, then we now have to consider not just what forces are acting on it, but where those forces are. I'm going to pick a direction to be positive. Rotationally, I'm going to call counterclockwise positive. So now, here's force 1, here's force 2. The torque exerted by force 1 is going to be 100 newtons. It's already perpendicular, times 2 meters, and that is in the negative direction. It's in the negative direction because if that's the only force acting, I'm going to get a clockwise rotation, and I just said counterclockwise is positive. So this is going to be negative 200 Newton meters. Torque from force 2, I have 100 newtons. It's already perpendicular. It's acting at a distance of 2 meters from the axis. If that's the only force acting, it causes the bar to rotate clockwise, which is the negative direction. So I'm going to get negative 200 Newton meters. The total torque acting on this bar is then negative 200, and negative 200 is negative 400 Newton meters, which is not 0. This is not in rotational equilibrium. So the next question, how do I make it be in rotational equilibrium? Well, I'm going to add one extra force, and it's going to be, I'm going to put it in purple to be an unknown force, and I will put it here. Force 3. I will put that at a location that is maybe 1 meter from the axis. So the torque produced by force 3, so this is the sum of torques from 1 and 2, the torque produced from 3 is going to be F3, because it's already perpendicular, times 1 meter, because it's 1 meter from the axis, and if force 3 is the only force acting, that causes my bar to rotate in the counterclockwise direction. So this thing is a positive torque. Now, if I want to put all my torques together, I'm going to say my total torque is going to be, I've got negative 400 Newton meters. This is torque 1 plus torque 2, and I should write these as vectors. I've got a negative 400 Newton meters plus F3 times 1 meter. And if I want this thing to not rotate, that whole thing has to be equal to 0. So F3 works out to be 400 newtons. If I instead move F3 to some other location, if I were to put F3 out here, now F3 is farther from the axis. If it's farther from the axis, then the torque that it produces gets amplified, so I would need less force at a bigger distance, or more force at a smaller distance. If I put F3 right on the axis, then this thing doesn't work at all. It doesn't have any torque because it would be acting at a distance of 0. Right now, F3 is here, and I get 400 newtons. I did tell you that I would do a bridge problem, and that's what's next. So a bridge problem looks like this. I have a bridge, and it is supported at its ends. Here is support A. Here is support B. This bridge itself has a mass of 10 kilograms. It's a toy bridge. And it's got a length of, let's go 4 meters. It's a really big toy bridge. Sitting on that bridge, I have a block. The block has a mass of 1 kilogram. And it's going to be sitting, a meter from the end of the bridge. And what else can I put? I will put over here, I will hang another block. We'll give this one a mass of 2 kilograms, and I'm going to hang it 1 meter from this far end. I would like to find the support forces at A and B. So the first thing that I'm going to do is draw a force diagram. Way back when, I was able to draw free body diagrams and all of them acted at the center of mass of the system. That's not going to be the case anymore. So now, the shape of this thing matters, the location of these forces matters. So I'm going to start drawing in what forces I have. Here's my FA. Here's an M1G. This thing is a tension, but it's going to be equal to M2G. Here's force B. And then the bar itself, the bridge itself, has a weight, and that acts at its own center. So capital MG. In order to do this problem, I need to pick an axis point. Now I can pick any number of axis points. I can actually pick any point I want to be my axis. Because if this thing is going to be in rotational equilibrium, it's got to be in rotational equilibrium about every axis. So I can pick anywhere that I want. That doesn't mean that everywhere is an equally good choice. The most likely places where I would choose an axis are at one of the ends where there's a force, or at the center of mass. I'm going to choose over here at the far left side, and I'll show you why as I go. So I'm going to choose that as my axis point. When I do that, now I'm going to label where every force is acting. This first force is acting at a distance of 1 meter from the axis. This one is acting at a distance of 2 meters from the axis. This one is at 3 meters, and this one is at 4 meters. I'm measuring just all those distances relative to the axis. Force A is acting at a distance of 0 meters. Now I'm going to start writing torque equations, really just the one. The sum of torques acting on this thing, I'm going to have torque from A, torque from mass 1, torque from the mass of the bridge, torque from mass 2, torque B. In thought, I could have every one of those. And they're all vectors. They are vectors, so the direction's important, so I'm going to have some kind of a direction that I call positive. I will go with, I've gone with counterclockwise the other times, I'm going to go with clockwise this time, just to shake things up a little. Now, the torque from force A is my force at A, which I don't know, times my distance, which is 0 meters. Torque from this one, this is going to be an M1G times 1 meter. This next one's going to be an MG times 2 meters. Next one is an M2G times 3 meters. And the last one is going to be a B times 4 meters. I want to look at the directions. On its own, well, first, here is the reason that I chose my axis at that location. In the end, I know I want this thing to be equal to 0. I want this thing to be equal to 0. I would like to be able to solve this, but I have two unknowns in here. By choosing my axis at this location, I'm able to take force A and multiply it by 0. That's going to get rid of that term completely, and the only unknown I'm going to have is B. That'll make things easier. So let me actually do that. This whole term goes away, equals 0. If I had chosen the far right side to be my axis, then B would be multiplied by 0, and A would be multiplied by something else. If I chose anywhere else, even the center of mass, then both A and B would survive in this equation, and then, well, then I've got to come up with something else. So I've got these. I would like to find B, and then I will work back and go and find A. Once I've got one of these, it becomes a lot easier. I just need to decide if these are positive or negative torques. This is my axis, so I have this big long bar, and I'm going to hold on to the left side of it, as though I'm holding on to, holding onto a pencil using just my left hand. I'm holding on to the end of it. Now looking at only force 1, only this guy, I'm going to ignore everything else. If only that is acting on the bar, and you can try this with your hand, hold your pencil up in your left hand, holding onto the left end of the pencil. Take your right hand and at the location of force 1, push down. Your pencil wants to rotate clockwise. We called clockwise the positive direction, so this thing is a positive torque. This second one, same story, is going to be a positive torque. And the third one, positive torque. Torque from B, if I hold this pencil, if I hold the left side of my pencil with my left hand, and I take my right hand and I push up on the far right side of the pencil, it wants to rotate counterclockwise, which means this thing is a negative torque. So positive, 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 and this one is negative. Now I can solve for this. So I'm going to move that to the other side, and I'm going to have B times 4 meters equals M1 is 1 kilogram times G. Let me just write these out. I get 1 kilogram, 10 meters per second squared, 1 meter, plus 10 kilograms, 10 meters per second squared, 2 meters, plus 2 kilograms, 10 meters per second squared, 3 meters. Left side, 10, this is, 1 times 10 times 1 is 10 Newton meters. 10 times 10 is 100 plus 2, times 2, that's 200 Newton meters. And over here, 2 times 10 is 20, times 3 is 60 Newton meters. So the whole left side is 270 Newton meters equals B times 4 meters. So I divide by my 4 meters, and I get right here that B is 270 divided by 4 is 67.5 newtons. Now when I want to find A, I could either set my axis here and redo the whole problem, or I can say, you know what, this whole thing isn't going anywhere. Let's just set my sum of forces equal to 0. Got A minus M1G minus Mg minus M2G plus B equals 0. So A will be M1G plus Mg plus M2G minus B, and that is M1G is going to be 10 newtons, M2G is 100 newtons, or Mg, and M2G, that's 20 newtons, minus my 67.5, 130 minus 67.5, looks like A will be 62.5 newtons, which is the smaller of the two, and that makes sense because more of my weight's on the right side, so B has to be holding up more. That's it. That's torque. That's the bridge problem.